Tesla has recently become the talk of the industry, especially with the debut of their new product. Audiences have been amazed by this next-generation robot's increased walking speed, noticeable weight reduction, and addition of sophisticated fingertip sensors. This is a noteworthy development in robotics. We examine the fascinating topic of robotics in this movie and showcase Tesla's second-generation bot's most recent advancements. We also talk about why one expert thinks the Tesla bot is in for a major surprise. Elon Musk said they hope to be operating in production productively by year's end, and I am convinced that this will happen in 2024. I am aware that Elon says prototypes are easy to make, even though manufacturing is challenging. However, both are accurate when it comes to humanoid robots. I've always thought they could make it really quickly. This expert provides a wealth of information because he founded 2 robot firms and has a good eye for market trends. Join us as experts uncover hidden Easter eggs and examine the smallest details of this groundbreaking study. Before we start, kindly hit the like button and subscribe to Tesla Stock News. All right, let's get going. When Tesla unveiled their new chatbot last week, the internet was ablaze with excitement. This next-generation marvel's significant weight reduction and faster walking pace pleased me. It's interesting to note that it now possesses powerful fingertip sensors and sophisticated hand talent, showing a major improvement in robotic capabilities. The expert raises interesting concerns about the weight of the bot, which was previously thought to be approximately 125 lb, and talks about the technical accomplishments made possible by its weight reduction of 10 kg. We contrast Tesla with other available robots, such Boston Dynamics Spot and Digit, to see where it stands. Scott delves inside the intricate workings of the bot's actuators and battery packs, showing the kind of sophisticated engineering needed to minimize weight without compromising functioning. Scott talks about potential areas for weight loss going into detail. His theories suggest that changes to the materials, including a move to plastics, and enhancements to the production process may have been essential. This modification impacts the bot's maneuverability, productivity, and weight. The question on everyone's mind is, how much does the Tesla bot weigh? Notwithstanding the obvious 10 kg drop, tech enthusiasts are nonetheless intrigued about the exact weight. When designing robots, Tesla puts greater emphasis on scalability and mass production than on utility. The second-generation bot seems ready for mass manufacturing because it is more advanced and simplified. These are not just cosmetic changes, but strategic ones. The bot's pelvis, for instance, has a streamlined shape that unifies its formerly separate front and rear sections into a single unit. This component reduction simplifies production and lessens the load, which could allow for rapid, cost-effective manufacture. The bot's improved walking speed, which is currently 30% faster, will be examined next. But in practical terms, what does this rise actually represent? Since the bot's speed hasn't been measured, we can only guess. Tesla claims that by restricting the bot's speed to less than 5 mph, safety will be ensured. A speed of roughly 3 mph, however, is more than sufficient for useful jobs like industrial labor. The bot appears to travel at a speed of about 1.5 ms, or slightly less than 2 mph, according to a speed analysis. This is the ideal pace for industrial environments where safety and efficiency are paramount. Is the Tesla bot ready to go into production right now? Its capabilities suggest that, despite serving primarily as a demonstration model at the moment, it is almost ready to be put to use as a practical tool in real-world situations. It's likely that Tesla had no more than 20 of these first-generation bots at first. Surprisingly, this tiny quantity proved to be sufficient for training with a lot of help from advanced modeling techniques. This refutes earlier theories that said training needed at least 100 bots to be successful. Actuators are an essential component of Tesla's robot development method because they allow movement. By November, these complex parts, which are necessary for the bot to function, should be ready for mass production. While FSD chips and batteries are easily obtained for Tesla, the primary focus for growing manufacturing is on actuators. We anticipate a steady increase in output levels in the future. Initially, several dozen bots may be deployed in various locations for testing and training. As the production process moves forward, we expect a significant rise in output. By the end of the following year, hundreds of these robots may be constructed, depending on how well the idea takes off. Tesla CEO Elon Musk has stated that these robots will be doing productive labor in factories by the following year. He was conservative in his results call forecast, but there's a strong likelihood that these robots will be operational by mid-2019. It seems that Tesla's humanoid robot can successfully navigate the challenging process of moving from prototype to mass production, which is often a challenging endeavor in the robotics industry. The robot's design is notable for its focus on safety and compliance, particularly in a production setting. For instance, prior concerns about the dangers of prodding and pinching have been allayed. Tesla's improvements, like as the addition of elbow protection and potential fabric coverings for more sensitive places, show their commitment to creating a robot that can safely work alongside humans. Notable advancements in terms of design improvements have been observed. The actuator's new location allows for a more compact wrist design, which improves the robot's dexterity and ability to maneuver in tight areas. The hands have been completely redesigned and equipped with new sensors for increased utility. The reshaped pelvis contributes to the creation of a more compact and effective structure. These modifications are not only aesthetically pleasing but also functional, even though its mechanics stay the same. The robot now walks with a more natural stride due to advancements in foot and hip mechanics. This heel-to-toe motion allows the robot to walk more quickly, demonstrating Tesla's commitment to continuous improvement. One clear distinction is the design of the bot's shoulders in the second generation. The servo axis for the shoulders was moved from its initial horizontal position to a slight 8-deg inclination, which increased the robot's range of motion and prevented issues such as the polar singularity. This seemingly insignificant adjustment significantly raises the robot's performance. The elbow mechanism has also undergone intriguing alterations. The new model's black material on the inside of the elbow raises the question of what it conceals. The elbow mechanism looks the same, but its packaging has been changed for convenience, possibly to accommodate wires or cooling needs. Our in-depth analysis shows that these design changes enhance the robot's functionality and safety in addition to its appearance. Now that the elbow is neatly covered in hard plastic and fabric rather than having protrusions that could cause a hazard, it is safer and more streamlined. It's possible that the robot's design was altered to accommodate a different battery setup. Regarding energy sources, there is conjecture that Tesla switched from using the smaller 2170 cells to the bigger 4680 cells. However, it's more likely that the robot uses the 2170 cells, albeit reconfigured for maximum efficiency given the energy density and supply variables. Cooling systems have also been taken into account. Fans are a familiar component. However, liquid cooling solutions might be utilized to maintain the proper temperature for the robot's internal circuitry. Another interesting discovery is the alteration made to the robot's tethering mechanism. The attachment points have been moved from the head to the shoulder area in order to effectively distribute the weight and prevent strain on the neck actuators. This improvement demonstrates rigorous engineering to ensure the robot's longevity and functionality. In a recent video, 3 Optimus models are seen at various stages of assembly. Claudia, Missouri first alerted us to this on John's channel. This astonishing finding demonstrates how swiftly Tesla is developing its robots. Much attention has been focused on the emergency off button, which is normally located behind the robot's neck. However, the new footage does not show the e-stop button, which has prompted concerns regarding its relocation. Upon closer inspection, the robot's lower back appears to have a red button, an unusual location for such a crucial component. We then examine how long the robot will last and how energy efficient it is. It has been questioned if the robots could operate for a complete 8-hour shift on a single charge. It's important to remember the incredibly high efficiency of Tesla's 2170 batteries, which are frequently seen in laptops, in order to allay this skepticism. A laptop may run for hours on a single battery while handling multiple processes and displaying visuals. It's feasible that the Optimus bot may continue to perform well for extended periods of time, further demonstrating the bot's power economy, given how much more sophisticated Tesla's complete self-driving system is. Despite being just around 1/3 the size of a Model S, the Optimus battery pack is still enough to propel a Model Y 10 miles at highway speeds. Consider the actuator that was used to raise a grand piano wing by half a ton in a demonstration. Lifting such a heavy weight requires a lot less power than one might imagine, which suggests that the robot battery could be able to maintain such tasks for a long period. Moreover, the possibility of continuous charging throughout operation presents further chances to maximize the robot's operational efficiency. In an interview with Gino, Tesla's lead designer hinted at future developments like wireless induction charging, which might allow the bot to refuel without a physical outlet. This technology suggests that Optimus may be able to operate constantly without needing human help for charging, together with advancements in capacitive and inductive charging from Quebec-based companies. While most makers of humanoid robots aim for a maximum operating time of 1.5 to 5 hours, Tesla seems to be aiming for an astounding 8 hours. The larger battery pack and highly efficient actuator provide an explanation for this, as well as the Optimus battery management system. However, many other robots have limited operating times because of their smaller batteries, which typically hold less than 1 kW.